All right, in this video, we are going to talk through some FRQs from Unit 2, specifically the 2010 FRQ problem number 5. So if you are trying to find these in OneNote, this is in the Unit 2 FRQs 2020 page, and you want to scroll down to find this problem right here. And if you have not tried this yet, you want to pause and take 15 minutes to try this problem. So again, this is from the Unit 2 FRQs 2020 page in our review sessions folder. So once you have tried these, then come back and join us and we'll go over the answers. So I'm going to start going over the answers. I will assume you've already done this problem. The part A, draw the electron diagram in the cell above. So we've got C2H2. So if you take a look at this one, if you think about our steps for drawing a Lewis dot structure, which we can review real quick, is you add up your valence electrons. So each carbon contributes 4 electrons, each hydrogen contributes 1. So you've got 10 electrons total. And if you start, then you start by connecting things with single bonds. At this point, I've only used up 2, 4, 6 electrons. So I'm going to go 7, 8, 9, 10. Notice how I don't have enough electrons to give my central atoms an octet. I have run out of electrons. So this is the case where you can turn those extra electrons into another bond. So instead of putting on that carbon, I'm going to turn it to a bond, and these ones, I'm going to turn that into a triple bond. So you end up with your carbons being triple bonded. And which of the 4 molecules contains the shortest carbon-carbon bond? Well, we know that as the bond order increases, the bond length is going to decrease. So the more electrons shared, the way I say it is the more shared electrons, the shorter the bond will be. And that bond will also have a higher bond energy. It's going to take more energy to break that bond because it's a stronger bond. So the one with the shortest and strongest carbon-carbon bond is going to be ethyne because it is a triple bond versus the other ones are all single bonds. Okay. If you look at C, this one asks you for the geometry around these atoms. And so if you're looking at a big molecule like this, there is no such thing as a shape name for this entire molecule. What we do is we name the shapes around the individual central atoms here. So like if we look at carbon X, whoops, there we go. This carbon, we'll notice it has 3 charge clouds surrounding it. So the name of the shape is going to be trigonal planar. And if the question had asked, we should also be able to describe the bond angles around it. Carbon Y has 4 charge clouds. It is tetrahedral. It's going to have about 109-degree bond angles. They also accepted trigonal pyramidal for this one, in case you were just looking at, this part of the molecule, where it'd say, oh, it's a lone pair, and then there's 3 hydrogens sticking out of it. Either one of those was accepted on this question. And then D, this is it's kind of a thermo, maybe a Unit 3 question, though, too, thinking about, it's more of a Unit 3 question, thinking about what happens during a phase change. So as we boil ethanol, what is happening? Well, whenever you have a molecular covalent substance, when you boil it, you do not break bonds. So no bonds are broken during like a boiling process. If you think about it like with water, right? We have liquid water. When we boil it, it's still H2O. I didn't break apart the H's and the O's. All I did was move the individual molecules further apart from each other. So what we do when we boil a molecular covalent substance is we just have to overcome the intermolecular forces. So taking a look at this statement right here, is this statement true or false? Well, this person said as ethanol boils, energy goes into breaking these bonds. Is that true or false? It is false. Why? Because no bonds are broken. No bonds are broken during the boiling process. All we're doing is overcoming these intermolecular forces. E, identify a compound that is nonpolar. So here I had the table down here again so we can look at these shapes. There are actually two molecules that are nonpolar. It is ethane and ethyne. So remember, molecules that are nonpolar are totally symmetric. They're the same all the way around. And so ethane and ethyne both fit that. If you look at F, this is an intermolecular forces question, thinking about solubility in water. So if we think about ethanol, if we take a look at down here, it's got an O bonded to an H. So ethanol is capable of hydrogen bonding with water. If you think about ethane thiol, this molecule is polar, but it's not capable of hydrogen bonding. So ethane thiol has dipole-dipole forces with water. It's important when you're thinking about solubility that you think about the intermolecular force that substance experiences with the water molecule. So imagine that a water molecule is over here, and you want to think about what is the attractive force between this molecule and the water molecule, because that's the thing that's going to make it, more or less soluble. The more attracted it is to water, the more soluble it will be. So this attraction is going to be stronger. So since it has a stronger intermolecular attraction to water, it is more soluble than your ethane thiol is. So that's what that question is looking for. Another problem that you can do if you have time is this one, the 2003 question, number 8. So you can take a moment to try that one if you haven't yet. All right, if we take a look at this first one for propanone, draw the complete structural formula. You would not be asked to do this on the exam this year, so maybe don't worry about this one. But it turns out this is what the structure would look like. And there are some different isomers that you could have come up with here. But this is the one that turns out that propanone does. You need one double bond in there to make this work. And then predict the carbon to carbon to carbon bond angle. So they're saying, like, what's this bond angle right here? So on this year's test, maybe you'd be given the structure and then asked, what's the bond angle? So you look at your carbon, it's got 3 charge clouds around it. It's going to be a 120-degree bond angle. You might also be asked the name of the shape. I would say it's trigonal planar. Another variation would be you could be asked what the orbital hybridization is. And since there's 3 charge clouds, we're going to hybridize 3 orbitals. So 1 s orbital and 2 p orbitals. So those are all variations you could be asked. And for B, this is an intermolecular forces question, and you want to explain the difference in the heat of vaporization. So if you look at propane, and sometimes it's helpful to make a little T-chart to make sure that you discuss both molecules, because it's really important whenever you're doing a compare-contrast question that you discuss both molecules in your answer. Don't just say because it can hydrogen bond. You need to be way more specific than that. Okay, so if we look at our 2 molecules here, propane and propanone, propane, this looks very symmetric. It looks like it is a nonpolar molecule. And if it's a nonpolar molecule, it only experiences dispersion intermolecular forces. Propanone, we looked at over here. Keep in mind this shape is trigonal planar, so really the molecule looks a little bit like this. So this molecule is not symmetric. It is polar. It has an oxygen side and then like a hydrogen side to it. So it is polar. There are no H's bonded to O's, so it can do dipole-dipole IMFs, no hydrogen bonding. So if we're explaining what's going on here, if you look at these delta H values, it looks as though propanone has a higher heat of vaporization because it has a stronger intermolecular force. And I would recommend, you write this out clearly. I'm just kind of jotting some notes here as I'm talking through it verbally. But on the test, make sure you write out a clear answer. And if you look at the second one, propanone and propanol. Again, if we can do a little comparison. Propanone we just talked about here, so we know that propanone is polar and has dipole-dipole forces. Propanol also looks polar. The difference here, though, is it's got an H bonded to an O, it looks like. So this one is capable of hydrogen bonding. And we notice that the one that can hydrogen bond has a higher heat of vaporization. So the same explanation would work here. Propanol has a higher heat of vaporization because that hydrogen bonding force is stronger than that dipole force. And that's the kind of thing you would want to write down. I wouldn't worry about this one. We're not going to have to draw structures, but here's another problem where you can see there's some hybridization in a sigma and pi question. So in this one, we've got a structure drawn. What's the hybridization on this carbon atom? Well, this carbon atom has 2 charge clouds on it, so you're going to hybridize 2 orbitals. So 1 s orbital, 1 p orbital. So it's sp hybridization. It's also, if we're curious, a 180-degree bond angle, and it is going to be linear. Remember, these 3 things are all related. The name of the shape, the bond angle, and the hybridization are all linked together. And then the sigma and the pi bonds. So what you want to remember is a single bond is always going to be a sigma bond. The only time you have pi bonding is if you have a double or a triple bond. And whenever this happens, the first bond is always a sigma bond. So if there's a double bond, what that means, you have 1 sigma and 1 pi. If there's a triple bond, you have 1 sigma and 2 pi bonds. So if we're going over here and counting our bonds here, the sigma bonds are the single ones. So I got 1, 2, 3, 4, 5, and then one of these 3 bonds is also a sigma bond. So it looks like I have 6 sigma bonds. If I count that right, let's see, 1, 2, 3, 4, 5, 6. Okay, and then these 2 extra bonds over here, those are pi bonds. So in that triple bond, the second and the third bond are both pi bonds. So that's a little bit about sigma and pi bonding. All right, so I hope that helps. Email me if you have questions.